Today's video is on volumes of known cross-sectional solids. And so a cross-sectional solid is a solid that's three-dimensional in shape, and it's formed by having the exact same cross-section, or, well, not the exact same cross-section necessarily, but the exact same shape, two-dimensional shape as each cross-section. So we need to make sure we know what a cross-section is. A cross-section is the shape we get when we cut straight through an object. So here are some examples. I took them from this website. We can take a cross section of a piece of celery. So we cut through a piece of celery, and the cross section would be this two-dimensional banana-looking shape. A cross section of this cylinder would be a circle. Cross section of the square prism, when we cut down this way, would be a square. If we cut across this way, it would be a rectangle. And then the pentagonal prism, it's a pentagon when we slice vertically. If we slice horizontally, it would be a rectangle. And one thing that's important about the pentagonal prism, and that's something that we'll be dealing with in calculus, is if we sliced it horizontally, the rectangles would be of different sizes each time we went across. That's something that's important because that's going to be happening in our shapes that we're dealing with. So as we are looking at this, for example, let's take a look at these two curves. So we have the red curve and the blue curve down here. If we want to make cross-sectional volume or a cross-sectional solid of all squares, what we would have here is, this is just one example of a square. And then as I take the limit of the amount of squares that I have, as I take that to infinity, it ends up basically forming a solid. So notice that the solid doesn't necessarily look like a bunch of squares, but when you slice through at each spot's going to look like a square. And that's basically what's happening. So notice that these squares are of different sizes. That's because the base of the square, the length of the side of a square, is going to be different at each of these spots. So notice that the length of the side of the square being different changes what the size of the square is at any particular spot. And if I go all the way from 0 to 1 for x, notice that my shape forms in that way. Now I can do the same thing with an equilateral triangle. So if I have an equilateral triangle, the same thing would be happening. I'm just taking a bunch of equilateral triangles and summing them up as we go to infinity. So here I get to n equals 100, but if I had infinity of those, it would be a solid. And notice once again that each of these is an equilateral triangle, the size of which is changing based on the function that I have. So if I have a different function that's showing up, each of these equilateral triangles is going to end up being a different size. Finally, I can do the same thing with semicircles. And I have this situation that's showing up here. It's a solid that kind of looks like a tunnel of some sort. And so that's basically visually what's happening. So we're going to talk about all these area formulas. That's because these are not the only area formulas you need to know, but these 5 just so happen to be used on this worksheet. And so we're going to talk about these. A square, most of us know what a square is. So if I call each side x or s, then the area would be side squared. If the side length represents the length of the function, let's call it f of x, or maybe f of x minus g of x or something, we would substitute that in for s here. And so you don't have to write down these parts because this is going to be different all the time. I'm just giving you an example of what would happen if I substituted in f of x for s. And f of x may end up being the difference between two functions or something. But I'm just kind of showing you what it would look like. A semicircle, typically the radius is half the diameter. Well, actually, that's true all the time. But if we're going to have the base of the semicircle be the diameter, and that's typically what ends up happening in these shapes, then the function length is actually uh, the length of 2 radii. And so the area formula for a semicircle is pi r squared over 2. And then typically, if substituting in some kind of value here, notice that the radius in this area function would only be half the length of the function that's on my paper, and so I would have to do some calculation adjustments. And that's kind of important to keep in mind, is that you always have to keep the context of the problem in mind. The rectangle with the height being half the base, so there's a picture diagram for it. The area formula for that would just be 1/2 base squared. And if the function length, or the length of the function on the x-axis, or on the actual graph, I shouldn't say the x-axis, but if I'm placing these rectangles uh, perpendicular to some axis, and this base is on the ground, then I would probably try and make my function uh, like deal with this base. Isosceles right triangle with the base as the leg. So what that means is that the base is the part that's on the ground in the shape. So if I'm looking at this, if I say the base, uh, what I'm referring to here would be this part. We call that the base. So that's the part that's on the paper, or on the ground, so to speak. We call that the base in these problems. So that means that the leg is going to be fixed by the function value, or the difference between two function values. And then if we have an isosceles right triangle with the part that's on the ground, the hypotenuse, that changes things a little bit. So the hypotenuse being on the ground, I would have to do this in one of two ways. This is the way that I wouldn't recommend, but it's probably the way that you would think about it at the beginning. Um, you would probably try to find these lengths, which will not be that easy given that h is going to be some kind of function. So you have some kind of function divided by the square root of 2. It's actually not horrible, but um, we end up with 1/4 h squared. But I'm going to recommend that you remember a formula from geometry, that a rhombus or a square, you can find the area of a rhombus or a square uh, by doing 1/2 times the length of each diagonal. And in a square, the diagonals are the same length. So this triangle is half of a square. So the bottom part would complete the square. So then we would end up with 1/2 of 1/2 d1 d2. So 1/2 times 1/2 h squared, which is 1/4 h squared, which is the same thing that we had up here. So you can either calculate it by finding the two legs of the right triangle, or you can calculate it by using the formula for a square and then just having it with 1/2 d1 d2. Okay, some examples. So if our cross-sectional areas are all squares, basically what's happening is I will have uh, this perpendicular, a cross section perpendicular to the x-axis. So I'm going to have a shape that basically ends up with a bunch of slices that are perpendicular to the x-axis, and each of these slices is going to produce a square. And drawing this is very hard, so I apologize in advance. But if, let's say, I'll draw one at 3, I have a square that's popping out of the paper. And if this is the square root of 3, because this function is y equals square root of x, then since this is a square, this length will also be the square root of 3. And so I have this square, and then I have another square that's coming out at every other spot. And so it basically sums up, I end up with a shape that kind of looks like um, what we just saw. So I would have a whole bunch of these squares. So this one's square root of 8, and this length would be square root of 8. So basically what I have is all of these squares, and then I'm going to sum it up with an integral. So as I go back, if I want to figure out the volume of this solid, I take a Riemann sum of all cross-sectional areas. And remember that a Riemann sum is an integral. So I will take the integral of this, the integral from a to b of whatever the area is at each spot of x dx. Or likewise, I could do it in terms of y if my cross sections are perpendicular to the y-axis. So I could go the integral from whatever my y values are of a of y dy. So this is basically what's happening. So what I'm going to do is I'm going to find what the cross-sectional area is at each spot. So since these are squares, the area is side squared. Now notice that the length of each side in this case is the square root of x. I want you to be aware that this is not true in every situation. It's only true in this situation because we're dealing with y equals the square root of x, and we're going down to the x-axis. So in other situations, you're not just going to be able to insert square root of x. You're going to have to insert whatever the function is minus whatever the other function is. Sometimes, especially last year, when I was doing this, these notes, people were thinking that square root of x worked all the time. That's not a good idea. So this only works in this particular situation because we're dealing with the function f of x equals root x, and we're going down to the line 0. So I just want to make sure that that's very clear. So the area function in this case is the square root of x squared, which is x. So the volume in this case is going to be the integral from 0 to 9 of whatever my area function is. So in this case, that's x dx. So this is x squared over 2 evaluated from 0 to 9. So my area is 81 halves. It's really not that hard once you figure out what the area of each cross section is. So once you figure out that the area of each cross section in this case is just x, all you have to do is integrate that and you're done. Okay, semicircles. So if I have a semicircle, this picture is not necessarily that easy, but I will try to draw one of them. And I'll pretend that this is at 4. So if that's the case, my radius is 2, or I'm sorry, my diameter is 2. And that's because, remember, my function in this problem is f of x equals root x. So my diameter is 2, which means my radius is 1. So if I'm thinking about this particular situation at 4, what I have is this is root x, which means that my radius in this particular problem is root x over 2. So I have one cross section. The area of a cross section is pi r squared over 2. So my radius is root x over 2. So I have pi times root x over 2 squared over 2. So this is pi times x over 4 all over 2, which is pi over 8x. So now I'm going to integrate that area function. So the area function is pi eighths x. So it's the integral from 0 to 9 of pi eighths x dx. Remember that we can pull the constant out if we want. So we have this situation. So this volume, I should probably label it as volume. So the volume is pi eighths times 1/2 x squared, evaluated from 0 to 9. I substitute in 9 and I get 81 halves times pi eighths. So it's 81 pi 16ths. 81 pi over 16 is my volume if I had a bunch of semicircles all summed up from 0 to 9. Rectangles. So let's take the rectangle situation. So this length would be 2 if I drew this at x equals 4, because once again, this is root x. And then this is half the length of root x, so that's just 1. So I'm going to find the area of each of these rectangles. So the area here is 1/2 times root x times 1/2 root x. So what I have in this particular case is I have, I don't know why I put it 1/2 at the beginning. Sorry about that. Remember that area is base times height, so I don't know why I put the 1/2 there. So base is root x, height is 1/2 root x, so this ends up being 1/2 times x. So that's pretty simple and straightforward. So I just integrate from 0 to 9 of 1/2 x dx. So that's 1/2 times 1/2 x squared, evaluated from 0 to 9, which is 1/4 times 81, or 81/4. So that's the volume. Finally, isosceles right triangles with hypotenuse as the base. So that's a 6. So the hypotenuse as the base means that the legs are kind of sticking out of the ground, so to speak. And then we have each of these volumes that we're going to kind of sum up. We have small right triangles over here, bigger right triangles over here, and then we just sum them all up and we get the volume of what's going on. So if this is root x, then these are root x over root 2. Those are the legs. And remember, you can find it by doing 1/2 times leg 1 times leg 2, or 1/2 leg squared. That's always a formula for the volume of a isosceles right triangle. But I would recommend using the formula for a rhombus. So 1/2 diagonal 1, diagonal 2, and then remembering that this is half of a rhombus or half of a square. And so each diagonal is the length of the hypotenuse. So I have 1/2 h1, and they're both the same hypotenuse. So h squared over 2, which is 1/4 h squared. And the hypotenuse is root x, so 1/4 root x squared, which is just 1/4 x. So I integrate 1/4 x from 0 to 9 dx. And I've done this a bunch of times, and I just have different coefficients out front. So this is going to be 81/8 when I'm all done. Finally, we have this case where we're now changing the function. So I have to understand what the function is. If I have a radius of 2, the circle would be x squared plus y squared equals 4. I have cross sections perpendicular to the x-axis. So basically what's happening is I have these vertical lines that I'm drawing, and then I want isosceles right triangles where the legs are one of the bases. So the legs are something that's on the ground. So I'm trying to find these areas, and then I'm going to stack all those areas up and turn it into a volume. And so what I have to do is I have to figure out what the function is. So I'm going to solve this for y. So y squared equals 4 minus x squared. Y equals the square root of 4 minus x squared. But it's important to understand that I have a plus or minus case. So the positive case is what I just traced in red. The negative case is what I'm now tracing in blue. And so what's happening is if I'm going from the top all the way to the bottom, I'm actually going from the positive case, so root 4 minus x squared, down to the bottom, the negative case, 4 minus x squared, negative root 4 minus x squared. So this total thing, the function, basically, are f of x minus g of x. That's an ugly looking g, but f of x minus g of x, that's going to be 2 times root 4 minus x squared. So this is going to be the length of each leg. So that's important that we know that that's the leg length. So now that I have that under control, now what I'm going to do is I'm going to find the area. So the area function is going to be 1/2 times 2 root 4 minus x squared times 2 root 4 minus x squared. And that's because that's how we find the area of an isosceles right triangle. Since these are going to be the same, we can just write it twice, or we could put a squared if we wanted to. So area equals 1/2 times 4 minus x squared. So the area function that we're going to be integrating is 2 times 4 minus x squared, which is 8 minus 2x squared. So now that I do that, I take the integral from -2 to 2. Notice that I'm going from -2 to +2 since I'm drawing these perpendicular to the x-axis. So I'm going from -2 to 2 of 8 minus 2x squared dx. So that's 8x minus 2/3 x cubed, evaluated from -2 to 2. I could do this pretty simply. So that's 16 minus 16/3 minus -16, which is plus 16, minus another 16/3, because it's basically 3 negatives going on in there. So I end up with 64/3 as my final answer. One other thing to keep in mind is that the volume of this, if I can think about this in terms of symmetry, the volume of this is going to be exactly the same on the left side of the y-axis as it would be on the right side, because the triangle that's formed over here would be exactly mirrored by another triangle that's formed over here, and that goes through all the way around. So really what I could have done is I could have done the integral from 0 to 2 of 8 minus 2x squared dx and multiplied it by 2 using symmetry. And so I'll just show you that it works real quick. 8x minus 2/3 x cubed, evaluated from 0 to 2. Then I multiply it by 2. So if I do this, I get 2 times 16 minus 16/3. And I can more easily, without having to deal with all these plus and minus sign situations that I might confuse, I still end up getting the same answer, 64/3.